Hello, everybody. I'm Qiaoya Wu, third-year grad student working with Yueshen on the multi-wavelength observations on reverberation mapping quasars, and I also work on the statistically analyzing the quasar spectral surveys. So today I'm going to show you my recent work that I've been working on for the last several months about using the photoionization model to understand the size-luminosity relation in the quasar broad-light region. So let's get started. Okay, so in the last century, people have discovered the quasars. So they realized that some of the point-like structure they observed in the sky are actually not stars but quasars. And they took the spectrum of those objects and they compare with the laboratory results and realized there are very obvious, strong, broad emission lines in those optical spectrum. And then they realized those objects are actually at a great cosmological distance. Okay, they are both on both sides. Okay, so since then, people have realized that those quasars are the most energetic and powerful objects in the universe. That's why I get into this area. It's very interesting. So, quasars have shown like very significant features across all the electromagnetic spectrum. So people to relate those spectral features to some of the components they observed in, we assume that exist in the AGN structure. So when you observe from different angle, you might see different components in the AGN structure. And so in the center of this AGN unified model is a supermassive black hole that's accreting stuff around it. And then go farther out is the accretion disk that all the hot matter orbiting around on that accretion disk and fueling the black hole accretion process. And then outside the accretion disk is a broad light region. That's some clouds floating around the disk, and they are moving at a very fast speed. Their speed can be up to several thousands kilometers per second. And these are are responsible for the broad emission line we observed in the optical spectrum. And then above the disk, there's narrow emission line. They are moving not as fast as the broad light clouds, so they don't have the very broad emission line feature. They have very narrow emission line feature. And then outside of that is the dusty torus. But here I'm not going to get into that. I'm just going to talk about the very inner region, the disk and the broad light region clouds in this AGN structure. So the most important parameter of the supermassive black hole is the mass of them. And there are several ways to measure that by direct imaging, like M87, or by observing the stars orbiting around the central black hole, like what we do with our own Milky Way. But for quasars, because they are very far away from us, it is very expensive to specially resolve them. So the best method we have is to use the reverberation mapping method. So, okay, sorry. I tried to get that move, but okay, it's done. Okay, so the basic of this method is to measuring the time lag between the center of between the continuum and the reprocessed flux from the broad light region clouds. And by obtaining the time lag between the two, you have the distance from the clouds to the center, and then combine with the velocity of that cloud, the velocity. So you can use this equation to obtain the black hole mass with some assumption, of course. And so the most remarkable result of the reverberation mapping method is the size-luminosity relation. That is, in 2013, Ben Sandor, they plot the size of the Hbeta emission line against the optical luminosity, and they realized that those two parameters are tightly correlated with each other. And they also fit for the slope, and they realized that the index is around 0.5. That's a very remarkable result, and that also laid the foundation of what we call single epoch variable mass estimator. So this method is, as you can imagine, it is way cheaper than reverberation mapping method, because you have to obtain a lot of light curves for one quasar, but this method only need to use one spectrum of the quasar. So when you take the spectrum, you have the luminosity of that quasar, and you combine with IR relation, and you have the size of the Broadlight region clouds. And in that spectrum, you have a lot of emission line, and you can measure the line properties of those emission line. And you can have the full width half maximum, which is related to the velocity of that cloud. So combine the luminosity and the velocity of that from that spectrum, you can have a good estimation of the black hole mass. So this method is very useful in a lot of quasar-related subjects. For example, you can use that to study the co-evolution of the supermassive black hole and its host galaxy. And also, it is very useful in spectral surveys. You can, for example, Sloan. And it is also very important for the high redshift supermassive black holes because it's impossible, almost impossible to obtain their light curves. So you can take their spectrum, it's in their rest frame UV spectrum. And you have the carbon-4 emission line. You can use the carbon-4 emission line to estimate the black hole mass by this single epoch method. And this method, despite it is very useful, but they still have a very large uncertainty, as you can see here. So we mostly use this method in 3 emission lines, Hbeta, magnesium 2, and carbon-4. And the y-axis is the single epoch method. The x-axis is from the RM method. You can see there's a very large scatter around it. Sometimes it can be up to 1. So it's still a large scatter around in this method. There's a lot of assumption we made in the way. So another very important application of the RL relation is that it can be used as a potential tool to probe the cosmology. So here in Watson 2011, you can see they plot the Broadlight region size against the redshift. So you know the Broadlight region size with RL relation. You have the luminosity of that quasar, and you compare the luminosity from RL relation with the flux you receive. You have the luminosity distance. So combine those two methods, you can use it to probe the cosmology. But you can see the uncertainty here is still very large, so we need more data and better constraints on the RL relation. And there's an extension of their work. Like you can see the constraint looks better than before. So
what's the green arrow on that one?
What?
What is the green arrow on that one?
You mean green?
No, the arrow on the right-hand side plot. So you see 74, 69, I think that is.
Those one?
Yeah.
This is some specific quiz. I believe they made some correction on there, but I'm not sure the details. Yeah. And this one also, they made some correction. They subtract the host contribution of their luminosity. Okay, so let's move on. So our relation, as you know, it is very important. It is like a holy grail in the IM regime. But so in the last decade, there are 2 campaigns that are very successful. They try to monitor the light curves of some agents. So the first one is called the Super Antenna Accretion Massive Black Hole Project, SIMBH project. You use a 2.5-meter telescope in Yunnan Observatory, and it monitors around 40 quasars. So combined with the other one, it seems very small because their work is like every 2 or 3 years they publish a paper and they talk about 2 or 3 quasars, and so they do that over and over again. So the number is not that much. And so they focus on the local universe and only on the super antenna accretion quasars, even though they claim that. But I checked their data, it's actually not that high. It's actually not super antenna accretion, it's just slightly higher accretion and with very bright quasars. So in the other project, it's called Sloan SDSS-RM quasars project. So they combine the data from several telescopes, but mainly from the SDSS. So they keep monitor the light curve for more than 800 quasars, and the redshift coverage is very wide. You can see from here, it extends from 0.1 to 3.5 or 4.5. So it also covers a very wide luminosity range, and so their result covers a very wide black hole mass range. So those two campaigns have realized there's trouble in the R relation. So in 2013, the relation is like tightly correlated with each other with a scatter of around 0.3, 0.4. But right now, the scatter gets much larger compared to the earlier ones after you add the new campaign's data. So what we want to do is trying to explain the scatter in this plot. So there are previous work working on this stuff. So they try do it one in 2019. They try to say what parameter does the IO relation related to. So they test down 8 spectral parameters shown here, and they plot the IO relation color coded by the 8 parameters they choose. So and so they thought that the first parameter, the R is the most important one, because you can see the farther away from that line, those data points are brighter. So they believe that this parameter is a major parameter that we can use to tighten the R relation, and they do that. They add the R into their fitting, and they realize it is getting tighter, but this relation is not driven by physics. It's just driven by some random parameter they choose, and they found the correlation. But their work does tell us that this parameter is very important, and this parameter is tightly correlated with the mass accretion rate. So we want to say what mass accretion rate plays in this IO relation. So to understand the mass accretion rate, we need to go a little bit into the accretion physics. So in the supermassive black hole accretion disk model, there are two famous models. One is the thin disk model, and the other one is slim disk model. So the thin disk model, also known as the standard model, was investigated by the Shakura and Savaier in 1973. So they made some assumption in their model. First, assumes it is a thin disk. So as the name suggests, you can ignore the height of the disk. You can just imagine it as a plane. And then they assumed that it's the matters on the disk is doing capillary motion. And thirdly, in order to balance the angular momentum loss, they assume that increased viscosity parameter called alpha viscosity. So that's the name alpha disk comes from. And they also assume that this disk is radiatively efficient, which means that the local energy on the disk is balanced out by the dissipation and the radiative cooling. And they took those assumptions into their equation, and they solved the disk equation analytically. And they find out the temperature profile is actually it's proportional to the radii. And that's the thin disk model. And later, people realize that when the accretion rate increases, this model become unstable, and because of the disk, the height cannot be ignored. It become comparable because of the increase of the radiation pressure. So people trying to find out new models. That is the thin disk model. So they Abramowitz, they didn't assume that it's a capillary motion. They assume it's a subcapillary motion. And because it's no longer a thin disk, so they have to consider advection into their consideration. And they take those assumptions into their model, and they solve for the disk equations. And they find that the disk indeed becomes thicker when the accretion rate gets higher. It's become comparable to the radii of the disk. And also the temperature profile also change. So remember, so the first thin disk model only stands when it's low accretion rate, and this one is for higher accretion rate. So we'll start with the low accretion rate example, because the thin disk model have been studied very well, and they have very good model to describe the SED from the thin disk. So we will combine our theoretic work with our observational work. We want to use the SED's photoionization model to predict the IO relation, and we want to see if there's any potential relation between the IO relation and the other observables as the emission line properties. And we also, so for the observational work, since it is impossible for us to observe the ionizing continuum that the brown clouds receive. So the best thing we can do is to use the high ionizing emission lines from the rest frame UV band to probe what the SED that the brown region receives. So we want to combine those two works and to see what's happening in the brown region IO relation. So to understand the theoretic work, we have to get the SED from the disk. So here is the SED from the quasar. We don't have to consider the jet, so we ignore this line. And since I'm just talking about the region that's within the dusty torus, so we don't have to consider theoretic. So we have three components we want to consider. The first one is the disk component, that's a multi-temperature black body radiation. And the second one is a warm Comptonized parameter that's used to explain the soft X-ray axis. And the last one is a corona component. So we use this model to generate our LCD on a grade of the supermass, on the mass and the accretion rate. So you can see from here, when the mass of the black hole increases, they have more energy in the LCD, and also the LCD is also shifting a little bit to the left. And this is when giving a fixed black hole mass and you change the accretion rate. So you can see the accretion rate shape changes a lot, and it becomes softer when the accretion rate increases. So, okay. So after we have the LCD, we want to take that to see what the Brouillard region would react when they receive such LCD. So we use a loc model, which is locally optimally emitting clouds. That is, we assume that the Brouillard region was consist of like each several clouds that's all floating in a certain region above the disk. So we use cold cloudy to simulate this kind of model, and you can see from the right. And so here are the line strings of 4 emission line and how they change when they ionizing photons and the hydrogen density change. So here is an illustration, and then after we get the emissivity from each cloud, we then integrate it over the radii. So here is also another illustration. So we can see how the flux for each single radii changes how the flux looks like for each radii. And after we get that, we can have we can integrate over the radii and can see the total light flux we can receive as an observer. So here's what we have for our relation. So the line in the background is what we modeled, what our model shows. So you can see they are, like, compared with observed data, they are very consistent with each other. Because of the model limit, we cannot, so the lower limit of our model accretion is minus 1.5. We cannot go deeper, but as you can imagine, the trend shows that if we have lower accretion rate, they will have more lines here. So our result is consistent with what we observed in the time lapse. And because this model is, we assume that universal hydrogen density and ionizing photons. So this model is like purely related to the LCD shape. So we believe that this kind of IO relation could be a potential tool to test on the LCD models and the accretion physics. And we want to compare that with observation, as I said before. So I dig into the HST UV archival data, and we do locate like 92 UV spectra for the low accretion AGNs with reverberation mapping, not all the AGNs. So here are the basic properties of those AGNs. So the gray color is those that we don't have their UV spectrum, and the color ones are those we do have their spectrum. So you can see that they are like the distribution of the black hole mass, the luminosity, and the time lapse located in this way. And so we first choose those quasars that have very close optical luminosity, like at 5100, and then we composite those spectrum and divide it by their accretion rate. So you can see here, like the blue color is the low accretion rate, the adenine accretion is lower than 0.2, and the green color is the moderate accretion, like slightly higher but not that high. So the composite spectrum shows that we normalize at the UV spectrum here, like 3050, and the higher accretion rate quasars give stronger line strengths. So which is also like consistent with our model prediction. So here are two like randomly selected LCD model. They have very different black hole mass and accretion rate. Of course, the higher accretion rate ones have lower black hole mass, and they have, so this one have higher accretion rate and lower mass, and this one have lower mass and higher accretion rate. They happen to have the very similar optical luminosity here, but you can see the ionizing energy is very different in for those two different SED models. So that's what we see in the UV spectrum. Even though they have the similar optical luminosity, their UV behavior is very different. So the next thing, so we want to compare our theoretic model with with the UV spectroscopy we observed. So here is what the local model suggests the line strength for full emission line, and this is what we measured from the real spectrum. As you can see, those two are very the trend is very close when they go this way. The line strength gets higher, so those show that our modeling was very successful. And if you look at the log model only, you can see that when the mass gate increases and the accretion rate increases, the line strength gets stronger. And so what we want to do is to compare. Oh, so this work is not fully finished. You can notice that there's 4 grids that's empty. Yeah, but because it takes a lot of computational resources, so I'm still doing calculating. So after we finish this part, we're going to compare what the line ratios dependence on the SED and on the RL relation, and maybe we can use this line ratios to correct for the RL relation to tighten up this relation, because it's very important for the single epoch and for the cosmology reason. And another reason is that, as I said earlier, the carbon-4 emission line is very important for the high Z supermassive black hole. So we want to use our UV spectrum to mitigate the uncertainty in the carbon-4 based single epoch black hole mass. And that's enough for the low accretion sample. And we go to the higher accretion samples. So the same batch, as I mentioned earlier, they focus only on the super active accretion black holes. And so in their work, they notice that, so compare the local agents from studied by Benz et al. And their new quasars, the new iron agents, you can see there's a clear offset between those two samples. And here I plot all the samples from the SDSS RM, local agent, and the same batch. So you can see when the accretion rate gets higher, it gets this very clear offset from the line that Benz et al. Gave. So we believe that the offset for the high accretion rate sample is because of the change of the geometry. So when the accretion rate increases, it's no longer a thin disk. It becomes a slim disk. Then the disk gets puffed up a little bit. So for polarization cloud, look at the region 2 in this plot. They cannot receive all the SED from the disk. They can only receive the SED from this region, outside of this line. Okay. And for an observer, we look at this region, and we don't have to care about the funnel structure. We can observe all the SED from the disk. So this is why we can, our observed SED is actually not what the polarization cloud received. So believe that this self-traveling effect is a reason for the offset we observed in the RL relation. And let's go back to the SED models. So here is the SED I showed earlier. And here is also the 2 low accretion rate sample I showed a few slides before. And for the high accretion one, because of the self-traveling effect, they cannot observe the very inner region of the disk. So the disk component would be be obscured a little bit, and also the more inner region, the soft X-rays, and also the corona would also decrease a little bit. So here's just a toy model. We need a better model to describe what the SED for those high accretion rates really looks like, because so we don't have a very good slim disk model right now. We are hoping to see if we can use our observation to put constraints on what the slim disk SED really looks like. And also I have to notice that. So all of them have fixed optical luminosity here. So even though we observe the same position as the x-axis in the RL relation, the y-axis will be very different because of the ionizing energy for the hydrogen is very different. So in order to understand that, we propose the observation on the UV spectrum of 16 high accretion agents with reverberation mapping results. And so those agents are shown here with those agents with the black circle. And we also, so those I just found out that this proposal just got approved today, so it's very good news. Thank you. And we're hoping to obtain data in the next year, and so we can be able to put constraints on the slim disk SED. And I do find several, like 4 or 5 high accretion agents in the HSD archival, and I composite their spectrum and compare with the low accretion rate example. As you can see, given the same optical luminosity, for the slim disk model, their line strength decreases compared to the moderate accretion rate ones. That proves our assumption that given the same optical luminosity, for the slim disk model, their SED drops for some reason. So that's my talk for today. So we first realized that IR relation is very important, but there's some problems in it. And then our model is consistent with our observations, and we can potentially use our models and our relation to put constraints on the SED models. And also for the low accretion rate and high accretion rate sample, they behave very different from each other. And there are the other work we would like to keep working on in the near future. Thank you.
We've got time for 1 or 2 questions. Kedar?
Yeah, so in your high accretion rate sample, which you just got approved for the proposal, HSC proposal,
yeah.
Are you planning to do like multi-epoch spectroscopy to see if you can model the accretion rate properly, and like how the line strengths change over accretion rate?
We do plan on doing the same measurements for those UV spectrum for high accretion sample, but right now there's no great model for the slim disk. There are models, but I checked, they use those models to fit for the stellar mass black hole accretion disk, but not for the quasars. And those who try to use the existing model to fit for quasars, they don't have very good results. So I would say right now there's no good model to describe the slim disk SED, but I think because of the line ratio is correlated to the SED shape, we believe that if we study the thin disk model fairly well, we may be able to put constraints on the slim disk SED shape.
And is there any guarantee these will remain high accretion rate quasars when you observe? Can they change the accretion rate over time?
You mean what? Sorry.
Like you proposed for a sample of high accretion rate based on previous observations, but there is no guarantee that they will remain as a high accretion rate quasar.
Yeah, they might change their accretion rate, but I don't think the time scale is very...
Okay.
Actually, related to that, what is the time scale between changing from high accretion rate and low accretion rate?
I actually have no idea, but I believe that it's not very soon within the several years, because the accretion flows would be existing for a long time.
Okay, let's thank our speaker again.